Hello all, welcome to the lecture. In today's lecture, we will start a new module on resonance spectroscopy. So, it can be spin resonance spectroscopy or magnetic resonance spectroscopy. These spectroscopies differ from most other kinds of spectroscopy. Here, the light matter interaction involves the magnetic field. So, the matter interacts with the magnetic field of light and not the electric field of light. The magnetic field is used to provide the energy level separations probed by the radiation. So, both these spectroscopies involve spin. So, spin is a fundamental property of an elementary particle. So, it is a fundamental property of any elementary particle. So, for example, electron is an elementary particle and electron has spin. So, the spin has no classical analog. So, the introduction of spin quantum number in quantum mechanics could explain many puzzling features. So, the spin is manifested by the presence of an intrinsic angular momentum. So, in this case it is the spin angular momentum which is represented by capital S, and this spin angular momentum is a vector. A convenient formalism is that spin angular momentum arises from the rotation of electrons around its axis, and the magnitude of this spin angular momentum, which is given by modulus of S, is h cross root over S times S plus 1. So, here this small s represents the spin quantum number. So, this means the angular momentum or the spin angular momentum is quantized. So, for an electron, the value of the spin quantum number, that is S, equals half. So, electron being a charged particle, it has something known as magnetic moment, which is denoted by mu s, which is also a vector, and this magnetic moment mu s is associated with the spin angular momentum, that is capital S. And the relation between this mu s and this spin angular momentum is given by mu s equals g of s E by 2 m sub E, then the spin angular momentum S. So, here the G s is the electron G factor, and the small e is the charge of electron, and m e is the mass of electron. So, we can write mu s equals G s E by 2 m E, and because S equals h cross root over s times s plus 1. So, we can write h cross root over s times s plus 1, and now s equals half. So, we can further write this as G s E by 2 m E h cross root over half times half plus 1. So, we can write now that this equals gamma h cross root over half times half plus 1, and the value of this electron G factor, that is G s, is 2.002. So, we wrote G s times E divided by 2 m E. So, G s times E divided by 2 m E, this we wrote as gamma, and gamma is known as the gyromagnetic ratio. So, we can see that this mu s is also quantized, and the quantity, that is E h cross divided by 2 m E, is known as the quantum of magnetic moment, and it is also known as Bohr magneton, which is denoted by beta. So, by comparing the two expressions in which we have beta and gamma, we can write G s beta equals gamma h cross. So, before proceeding further, let us study the general properties of angular momentum. So, the angular momentum is in general denoted by J. So, let us study the general properties of angular momentum in quantum mechanics. So, the first property is, and we saw this during our discussion on this spin angular momentum just like couple of minutes back, the angular momentum vector, that is J, the vector J, has a magnitude which is given by, so the magnitude of J is given by h cross times root over J times J plus 1, where the small j is a quantum number, which is the angular momentum quantum number. That means, it is a quantum number characterizing the angular momentum. So, secondly, there are only certain possible orientations of the vector, that is the vector j, with respect to the z axis, and this is known as space quantization. So, let us say if the vector j, so this is our z axis, and let us say the vector j makes an angle theta with the z axis. So, this is our vector j, and the magnitude of j equals h cross root over j times j plus 1. So, the possible values of theta will be such that the z component of j, so the z component of j, so which we can denote by this length, that is the projection of j on the z axis, which we can call j z, will also be quantized. So, we can write j z equals j cos theta, and because it is quantized, it is m j times h cross. So, this m j is a quantum number. So, we can write that m j equals root over j times j plus 1 cos theta. So, we have seen this during our discussion on angular momentum in rotational spectroscopy. So, from this relation, it follows that m j quantum number can have the following values. It can have values of like m j can be take the values of j, j minus 1, j minus 2, dot dot dot, 0 is another value, and it will go up to minus j. So, in total there can be 2 j plus 1 values of m j. So, when a particle with angular momentum j and magnetic moment mu j, so the particle has angular momentum j and magnetic moment mu j. So, mu j is given by gamma, is a gyromagnetic ratio, times j. So, when this particle is placed in a magnetic field applied in the z direction, then for an orientation of j. So, let us say this is my z direction and the magnetic field is applied in the z direction and our j is in this direction. So, then for an orientation of j, which is this, a torque acts on the magnet, which is given by d j dt equals mu j cross b, and because mu j is given by gamma j, we can write this as gamma j cross b or gamma j cross b. So, the vector j can be written in terms of its Cartesian coordinates. So, we can write the vector j as I hat j x plus j hat j y plus k hat j z. So, here this I, j and k, so this I, j and k are the 3 unit vectors along x, y and z directions. And for the magnetic field B, because B is applied along the z axis, we can write B equals k hat B, and this is because it is only along the z axis. So, B x equals 0, B y equals 0 and B z equals B. So, now let us look into what do we mean by a cross product. So, let us say we have two vectors, one is A and the vector A is given by I hat A 1 plus j hat A 2 plus k hat A 3. And we have another vector that is B, which is given by I hat B 1 plus j hat B 2 plus k hat B 3. So, now if we need to compute this A cross B, so the A cross B we can write is as I j k, then A 1 A 2 A 3 B 1 B 2 B 3. So, this A cross B will be, you have to write I, then A 2 A 3 B 2 B 3 minus j A 1 A 3 B 1 B 3 plus k A 1 A 2 B 1 B 2. So, now we have to compute j cross B, and this is our vector j and this is our vector B. So, if we compute, let us say j cross B, what we get is, so we can write I j k, this is j x, j y, j z, but for B this I and j components are 0 and we only have B here. So, this will be equal to, what we will get is I times j y B minus j times j x B. So, we can write that I, because j equals I j x plus I j y plus I j z. So, this d j d t we can write as I d j x d t plus j d j y d t plus k d j z d t, and it will be the same thing that we have computed, but only multiplied by gamma. So, we can write this as gamma minus j times j x b plus I times j y b. So, we have this expression I d j x d t plus j d j y d t plus k d j z d t equals gamma times minus j j x b plus I j y b. So, if we compare this expression, we get d j x d t equals gamma j y b and d j y d t equals minus gamma j x b, and also we can see that d j z d t equals 0. So, this third equation, that is d j z d t equals 0, indicates that j z is a constant. That means, j z is conserved. but j x and j y depend on time. So, using these two expressions, we can write that j x d j x dt plus j y d j y dt. So, d j x dt is, so it will be gamma j x j y b minus gamma j x j y b. So, this will be equal to 0. So, because j x d j x dt plus j y d j y dt equals 0, we can further write this as half d of j x squared dt, because if we have j x squared and then take the derivative is 2 j x. Now, we are dividing by half. So, we can write this term as half d j x squared dt and this term as plus half d j y squared by dt equals 0. Or in other words, what we get is d of j x squared plus j y squared dt equals 0. So, this expression d of j x squared plus j y squared dt equals 0 tells us that j x squared plus j y squared is a constant. Hence, because we have j z squared which is a constant and j x squared plus j y squared is also a constant. So, we can write j squared which is nothing but j x squared plus j y squared plus j z squared. So, this is a constant. That is, when placed in an external magnetic field, the j squared and j z are constants of motion, but j x and j y change with time. So, we will end this lecture here. In the next lecture, we will discuss the consequences of what we have learned today because of this j squared and j z being constant.